Okay, so this is the solution key for Unit 2, Reactions in Aqueous Solutions, problem set 4. So I went through and I wrote most of the balanced equations out just to save a little time. Notice balanced equation, the phosphoric acid and sodium hydroxide, and I wrote down concentration of phosphoric acid, the volume of sodium hydroxide in liters, and the concentration. And the question is, what volume of the acid am I going to need to completely react with 50 milliliters of the 0.2 molar sodium hydroxide? So I'm going to go ahead with this one and just start my stoichiometry. I'm going to go ahead and start with the volume of sodium hydroxide I have. So I want to figure out how many moles of sodium hydroxide I have. I have a 1-to-3 ratio between phosphoric acid and sodium hydroxide. So I want to figure out how many moles of phosphoric I need so that I completely use up my sodium hydroxide. All right, so changing my volume to liters, we're going to start with 0.05000 liters of sodium hydroxide. And according to my molarity that I was given, I know I have 0.200 moles of sodium hydroxide for every 1 liter of solution. I also have a mole ratio of 1 mole of my acid, H3PO4, for every 3 moles of sodium hydroxide. And then last thing I'm going to do is I want volume of phosphoric acid. So I'm going to go ahead and use my molarity, except I'm going to have my volume on top. I know that 1 liter of my phosphoric acid has 0.200 moles. That's going to give me a total of 0.016667 liters. I went ahead and I just changed that to milliliters. You could leave it in liters if you want to because it doesn't specify in the question. All right, next question. What volume of 0.115 molar perchloric acid solution is needed to neutralize 50 milliliters of a 0.0875 molar sodium hydroxide? So remember the word neutralize, and when they say completely react, they mean the same thing. Completely react, neutralize, equivalence points. Those all really are saying the same thing. We see it down here on this one too. So again, we're going to treat this the same way. We're going to start with my sodium hydroxide, 0.05000 liters of NaOH. And the concentration gives me 0.0875 moles of NaOH for every 1 liter of NaOH solution. The mole ratio here is actually 1-to-1. So we have 1 mole of the HClO4 for every 1 mole of NaOH. And then I know that my concentration here for my acid is for every 1 liter of HClO4, I'm going to have 0.115 moles. That gives me 0.0380 liters of HClO4. And I put 28 here. So recalculate that. See if you get 28 or 38. That actually might be a typo. I'll have to check that later. So, but I think my calculation is right. So I think it's supposed to be 38.0 milliliters. And I'll go back and fix that later. All right, so let's take a look at the next one. 2HCl, let's see, here's my concentration. We're going to completely react it with 2.87 grams of magnesium hydroxide. So we're going to go from moles of or grams of magnesium hydroxide to moles of HCl, and then to volume again. So 2.87 grams of magnesium hydroxide. And the molar mass from the periodic table is going to be 58.32 grams. Mole ratio here is 2 to 1. So 2 moles of HCl for every 1 mole of magnesium hydroxide. And then I want volume again. So I'm going to go ahead and use the concentration of my HCl. And I know for every 1 liter of HCl, we're going to react it with 0.128 moles of HCl. Okay. That gives me approximately 0.769 liters, or hopefully 769. Oh, I did again, milliliters. So check that answer in 2A, just double check that. And then again, when we talk about neutralizing, what we're doing is we're adding hydrochloric acid to the magnesium hydroxide until we completely use them both up. So there's no excess reactant, no limiting reactant. And we use an indicator that will tell us it's changing from a basic solution to right before it changes to an acidic solution. So we'll have some sort of indicator that'll tell us when we get to that equivalence point. Okay, let's take a look at number 3. In number 3, they gave us the balanced equation. You spilled some sulfuric acid on a lab bench, and you're going to neutralize it again by sprinkling some sodium bicarbonate, which is a base, mopping it up. The sodium bicarbonate reacts according to the equation that's there. This is an acid-base reaction. One of the reasons you can tell is you have the water being produced right here, and basically the base part right here is accepting a proton. And so you're producing water and you're producing carbon dioxide and a soluble salt. So it's added until the fizzing is complete. It says if 27 milliliters of the sulfuric acid is spilled, what is the minimum mass of baking soda you have to add to neutralize it? So here's what we're looking for. We're looking for the mass of the baking soda. We know that we spilled 27 milliliters of the sulfuric acid, and we know it's pretty strong at 6.0 molar. So let's go ahead and start with the volume that we spilled, change that to how many moles we spilled, and then we can use our mole ratio and then find grams. So we've got 0.027 liters of our sulfuric acid, H2SO4. Now, we know that there are 6.0 moles of sulfuric acid for every 1 liter. Then we knew we have a 2 to 1 ratio. So there are 2 moles of baking soda needed for every 1 mole of sulfuric acid we spilled, H2SO4. And then to convert it to grams, we just need molar mass. 84.01 grams of baking soda for every 1 mole of NaHCO3. So hopefully adding about 27.2192 grams would do it. Significant digits on this one. I really see 2 significant digits there and there. So I stuck with 2 and just said 27 grams of NaHCO3. That's it. All right. Question number 4. I really should have left a little bit more space for this. This is a good problem. There are some FRQs that kind of resemble this. And the key to this one, and what I want you to focus on, is this word impure. That implies that it's not all magnesium hydroxide, but you're dissolving it in 100 milliliters of a 0.205 molar HCl solution. The excess acid is then going to be neutralized by adding some sodium hydroxide. So basically, you're going to dissolve it in the HCl, but some of the HCl is going to be in excess. And so you're going to add some sodium hydroxide to that to neutralize it. We want to calculate the percent by mass of magnesium hydroxide in the sample. So this is actually a pretty intense problem because we're actually going back to this 0.5895 grams, and we need to figure out how many grams of that was actually magnesium hydroxide. Because not all 0.5895 grams of it was magnesium hydroxide. Some of it was something else. We don't know what. It just says is impure. They don't tell us what that impurity is. So they also have to kind of preempt this with assume that it is only the substance reacting with HCl solution. So they're saying assume magnesium hydroxide is the only thing in that impure sample that's going to react with HCl. So got a lot of stuff going on in this one. So the first thing we need to do is we need to figure out really how much of the acid, we need to figure out how many moles reacted of the magnesium. So here's what we're going to do. I'm going to look at reaction 1 first. And reaction 1, that's the reaction between the magnesium hydroxide and the HCl. And we're producing magnesium chloride from this, Cl2, and some water. But we also have excess HCl, and that's really important in that first reaction. I think I've got everything balanced out. We'll put an L there, so I think we're good there. This is impure, and we really don't know what mass we had that was pure magnesium hydroxide. We know this was our impure sample, but we really don't know how many grams of that was magnesium hydroxide. But we do know we added 100.0 milliliters of a 0.2050 molar solution. So I'm going to kind of write that right there to keep track. Now, the second part of this, so really the second reaction, was this excess HCl. Some of that HCl then was reacted with some sodium hydroxide. And the key here is for neutralization. So we basically reacted enough sodium hydroxide to react with how much excess HCl was there. Now, a couple things right here. Again, we know the concentration of the HCl was 0.2050 molar. We just don't know how many more moles of that HCl was left. We also were given some information about the sodium hydroxide. We know that we have 19.85 milliliters of this, and the concentration is 0.1020 molar. All right. Now from here, we're going to produce some sodium chloride, NaCl, aqueous. This is a strong acid, strong base, and H2O. And at that point, we are neutralized, or it completely reacted. So here's the thing. We know that we reacted all 19.85 milliliters of the 0.120 molar sodium hydroxide with the hydrochloric acid, and that used all the excess hydrochloric acid up. So I'm actually going to work backwards. I want to figure out how many moles of HCl I had in excess. So let's go ahead and we're going to work backwards, starting with reaction 2. We're going to take our milliliters here. So we've got 0.01985 liters of NaOH. And I'm going to figure out how many moles I added. So I know 1 mole. Oops, sorry, my bad. Not 1 mole. 0.01020 moles of NaOH are in every 1 liter of NaOH, because that's the concentration I have. And I also know I have a 1 to 1 mole ratio here. So I know 1 mole of HCl for every 1 mole of NaOH was reacted. So once I figure out how many moles of sodium hydroxide I reacted, that's the same as the moles of hydrochloric acid I had there. I'm going to go ahead and use this concentration later on, but I don't need it here. Although I could use it to figure out what volume maybe was in excess. But for this part, I just want to know moles of HCl. So let's go ahead and calculate that. I think it's 0.00200247. And that's how many moles of HCl were in excess, which was interesting. So that's one way I'm going to look at it. Again, you could figure out how many milliliters of HCl didn't react, but then you're going to have to go back to moles anyway. So here's what we've got now. So now we know this is how many moles were in excess. I want to go back and figure out how many moles I had of HCl initially. So initial moles of HCl. If I figure out how many moles of HCl I started with and subtract what was in excess, I can figure out how much it took to react with my magnesium hydroxide. So again, really, really kind of complicated thinking question, but just kind of follow what's happening as we're working backwards. It's kind of a lot of fun to think about it. All right, so we've got the initial volume of HCl that we added, so 0.01000 liters. That comes from right up at the top. Did I do that right? 100 milliliters. Yeah. Times, oops, nope, see, too many zeros. 0 point, there we go. Only move it 3 times. There we go, 1, 2, 3. All right. Right. 1, 2, 3. All right, liters of HCl. And then we're going to multiply that by the 0.2050 moles of HCl for every 1 liter of HCl. And that's going to give me 0.02050 moles of HCl. And that's initial. Now, I need to figure out how much of that initial concentration I actually used. So I'm going to subtract basically what I didn't use. So I'm going to take, let's do HCl used. And so we're going to do the 0.02050 moles of HCl. And we're going to subtract 0.0020247 moles HCl. I keep a lot of sig figs in my work and I don't round till the end. So just kind of check that out a little bit. That gives me 0.018473 moles of HCl used. That's how much actually reacted with my magnesium hydroxide. So now I'm going to go through and I'm going to use that 0.0184753 moles of HCl that reacted originally. And I know my mole ratio is 1 to 2. So for every 1 mole of magnesium hydroxide that reacted, I had 2 moles of HCl in my ratio. And then finding the mass, 1 mole of magnesium hydroxide, this is right anyway, has a mass of 58.32 grams of magnesium hydroxide. Woo, that means 0.53874 grams of magnesium hydroxide reacted. All right. So thinking about sig figs here just really quick, it looks like I'm using four. So 1, 2, 3, 4. I think I had pretty much 4 sig figs through this whole thing. So we're just going to go ahead and say 4 sig figs, because even when I subtracted, let's see, 1, 2, 3, 4, I would have went to 2, 3, 4. I would have went to this place value. So yeah, we're safely going to say 4 there. So mass percent. See, we're not done yet because they asked us for the percent by mass, right there, of magnesium. So if I have 0.5895 grams of my impure magnesium, my percent MgOH2, slide this up, by mass, because when they say percent, they're talking about percent by mass. I'm going to take my grams of magnesium hydroxide that I actually reacted, 0.53874 grams reacted, divided by the mass, that was my impurity, 0.5895 grams of impure stuff. Sample. And then we're going to multiply that by 100. And we get approximately 91.39%. There we go. Ooh, that was a good one. All right. I might take a little break here and come back. Okay, question number 5. We're going to write a balanced, complete, and net ionic equation. So we've got what mass of sodium chromate is required to precipitate all the silver ions from a solution of silver nitrate. So we're going to write out our balanced equation first, CrO4, and we're going to react that with silver nitrate. And our products are going to be NaNO3 and silver chromate, Ag2CrO4. Okay, so assuming all of these are in water, our ions, spectator ions, are going to be sodium and nitrate. So that's our precipitate. And we're precipitating out all the silver ions. So they're asking us to write a complete ionic and net ionic. So here's our complete ionic equation, would be the 2 sodium ions, aqueous, and the chromate, 2 minus, react with, so you need to put a 2 in front of there to balance it out and a 2 in front of there to balance it out. So let's give me 2 silver ions and 2 nitrate ions. And then my solid, Ag2CrO4, solid. So my net ionic equation is just minus the Na plus and the NO3 minus. So it's my chromate, my silver, forming my silver chromate. So now we're going to solve the problem. What mass of sodium chromate is required to produce all the silver ions from 75 milliliters of a 0.1 molar solution of silver nitrate? So we know that we've got 0.100 molar and 75 milliliters. I want to know how many grams of that it's going to take. All right, so we've seen one like this before, right? We're going to take our volume, 0.0750 liters of the silver nitrate. And we know that there are 0.100 moles of silver nitrate for every 1 liter. And we know that our mole ratio is 1 to 2. So 1 mole of Na2CrO4 for every 2 moles of silver nitrate. Now to find mass, one more step, molar mass, 161.98 grams of Na2CrO4 for every 1 mole of Na2CrO4. So that gives me about 0.607425 grams. It looks like I've got 3 significant digits pretty much throughout. So that's going to give me 3 significant digits. So 0.607 grams of Na2CrO4. Okay. All right, question number 6. What mass of silver chloride can be prepared by the reaction of 100 milliliters of 0.2 millar silver nitrate with 100 milliliters of some calcium chloride? So we kind of just want to know what mass of precipitate we're going to get from this. So silver nitrate is AgNO3, that's aqueous. We're going to react that with some calcium chloride, CaCl2, and that's aqueous. We're going to get silver chloride, AgCl, that's our precipitate. And then we've got calcium nitrate, CaNO3, 2 of those, and that's going to be our spectator ions in that. So balancing this out, 2 there and a 2 there. Sometimes it's a good idea just to step back and look at the information that you're given and see if you can reason it out without any major calculations. And if we look at the silver nitrate, we've got 0.20 molar solution. We've got 100 milliliters. And then for calcium chloride, we have the same volume, but a little bit lower concentration, 0.15 molar concentration in 100 milliliters. So if I'm comparing moles of both of these, I'm going to take volume rate out of the equation. I can kind of just ignore that and focus on the fact that my concentrations are different for these two, but I actually need twice as many moles of silver nitrate as calcium, and I don't have that. This would have to be 0.3 molar or 0.3 moles in 100 milliliters of solution to be twice the amount. This is 0.15 molar. Now, if you want to do a calculation, you could do that. You could change this to moles, right? So using your formula, you would have 0.02 moles. This would be 0.015 moles. And you can see I need twice as much of the silver nitrate and I don't have twice as much. So this is actually going to be my limiting reactant. So AgNO3 ends up being my limiting reactant. So if you can do that without doing a big long calculation, that might save you a little bit of time. Knowing that that's my limiting reactant, now I can just use this to get to mass of calcium nitrate. So starting with my volume, 0.1000 liters of silver nitrate. And again, our concentration is 0.20 moles per liter. And that's of AgNO3. So I'm going to write it up here. Now, my mole ratio is actually 2 to 2. You can reduce that 1 to 1 if you want to, but 2 moles of silver chloride for every 2 moles of AgNO3. And then molar mass, 143.32 grams for every 1 mole of AgCl. And that gives me approximately 2.9 grams of AgCl. When you calculate this out, I think you get 2.8664 grams. This rate here is 2 significant digits, so my concentration is 2 significant digits, so I went ahead and just rounded to 2.9. All right, on to question 7. We've got some tartaric acid, 2 acidic hydrogen, so it's diprotic. The acid is often present in wines and precipitates from solution as the wine ages. A solution containing an unknown concentration of the acid is titrated, there's that word again, with some sodium hydroxide. We know that we need 24.65 milliliters of a 0.25 molar sodium hydroxide solution to titrate both acidic protons in 50 milliliters of tartaric acid. So we're going to write an equation first for this neutralization reaction, and then we're going to calculate the original concentration of the acid. So we've got our acid, H2C4H4O6, and we're adding sodium hydroxide, that's what we're titrating with. We've got sodium, let's see, tartrate is our soluble salt, and we're forming water. So let's go ahead and we'll put some physical states on here. Aqueous. This is sodium and a polyatomic ion, so we know that's aqueous, and then we've got water. So acid-base reaction. To balance this out, we definitely need 2 of those, and we're going to get 2 waters out of that. So we know we added 50 milliliters. We want to find the concentration of that acid. So we know that we've got 24.65 milliliters is what we added of the 0.2500 molar solution until we got to our what we call equivalence point, or until we neutralized our solution. So we're going to start with our 0.02465 liters of our sodium hydroxide. We want to figure out how many moles of sodium hydroxide that is. And so we know we have 0.2500 moles for every 1 liter of sodium hydroxide. And so that'll give us how many moles of sodium hydroxide we added. And we know we need 2 moles of sodium hydroxide to neutralize 1 mole of tartaric acid. So it's 1 mole of our acid, H2C4H4O6, for every 2 moles of sodium hydroxide, NaOH. I'm going to go ahead and I know that's going to give me moles. So that's going to give me whatever I get from moles. I'm going to go ahead and multiply that by 1 over the volume, 0.0500 liters, because I know when I get whatever moles I have here that I'm just going to divide by volume. My concentration for molarity, I want my units to be moles per liter. So I know this is going to give me moles. I know this is my volume. And so I'm just going to go ahead and divide right now. That gives me 0.06163 molar tartaric acid, H2C4H4O6. So don't hesitate to calculate, your moles here and then plug it into the formula. But I just went ahead and put my volume on right there and got my answer. I stuck with 4 significant figures because it looks like most of my measurements in my calculation are 4 sig figs. So stuck with it. All right, question number 8. We've got some nickel 2 sulfate and we're mixing it with some potassium hydroxide. We're going to get a precipitate and we're going to get some potassium sulfate. That's going to be aqueous. The precipitate that forms is nickel 2 hydroxide. And this is a precipitation reaction. We've got an aqueous nickel 2 sulfate, some strong base here. We're getting a soluble salt right here, and we're getting a precipitate. So we just have a precipitation reaction. And so our precipitate is NiOH2. That's our solid, nickel 2 hydroxide. Limiting reactant. So here's what I'm going to do. I always kind of look ahead at the next question. This question is asking me how many grams of precipitate form. So I'm going to figure out which one of my reactants is going to give me the least number of moles of precipitate, and then I'll go ahead and calculate grams from there. So starting with my nickel sulfate, I have 0.2000 liters of nickel 2 sulfate. And then we'll go ahead and we'll say 0.150 moles of nickel 2 sulfate for every 1 liter. And then I know that 1 mole of NiOH2, which is my precipitate, is going to be formed every time I use 1 mole of NiSO4. And that comes right from the balanced equation right here. It's a 1-to-1 mole ratio. That gives me 0.0300 moles of NiOH2, nickel 2 hydroxide, if I use all of this reactant up. So let's see what happens with the other reactant. The other one's potassium hydroxide. We've got 0.1000 liters of KOH. And our molarity, 0.200 moles of KOH for every 1 liter. And we also know that 1 mole of nickel 2 hydroxide will be produced for every 2 moles of KOH. And that's probably the difference here, because this gives us a little bit less, 0.0100 mole of nickel 2 hydroxide, NiOH2. Need to put that extra parenthesis in there. So that means potassium hydroxide is our limiting reactant. So we're going to use that number down here, 0.0100 moles of our precipitate, and figure out how many grams we made. Molar mass is 92.71 grams, NiOH2, and that's per mole. So that's going to give me 0.927 grams of NiOH2. All right. That's kind of the easy part with this one. The next part is concentration of each ion. So kind of keep track of the fact that in this beginning solution, we have some Ni2 plus, some SO4 minus, we have K plus, we have OH minus. So right away, if we take a look at our spectator ion, our spectator ions, sulfate and potassium. So one of the things we could do is tackle those two first and just figure out what their new concentration is. I'm going to go ahead and do sulfate, I think, first. Originally, sulfate had a concentration. Let's see, over here, there it is. My original concentration for sulfate ions was 0.150 molar. And the original volume of solution was 200 milliliters. I want to know what my new concentration is and my new volume. My new volume is when I added these two together. So my new volume is 300 milliliters. And you know what? I want to preface one more thing, because when this breaks up into ions, I get 1 part nickel ion and I get 1 part sulfate ion. That's how come I can say my original concentration of sulfate was 0.150. It's really because it's a 1-to-1 mole ratio. If I had like 2 SO4s instead, I could not say that I would have double the SO4 concentration. So just kind of keep that in mind. I'm really going by the fact that that's a 1-to-1 mole ratio there. When I do this, I end up getting 0.100 molar for my sulfate, SO4 minus. That's my new concentration. Remember, moles don't change. So since the volume of the liquid went up, or the volume of the solution went up, the molarity is going down. And so I'm going from 0.150 down to 0.100. I would expect my potassium to go down as well. And again, up here, I have a 1-to-1 ratio. So my potassium ion concentration is also 0.200 molar. So originally, I've got 0.200 molar KOH, or K plus, and I had 100 milliliters of it. My new concentration at 300 milliliters, that's what we're going to calculate. And we get about 0.0667 molar K plus. All right, so we answered 2 of the questions. I'm going to tackle hydroxide next. This one right here, not only was this part of the limiting reactant, but it was also part of the precipitate, PPT. That actually is kind of a good thing. Since we know it's part of the limiting reactant, we know that for hydroxide, that we used it all up. It was part of the limiting reactant and was used to form the precipitate, PPT. So we literally have no hydroxide ion left. All right. Here comes the hard part. It's the nickel, because we did not use all the nickel up, right? So I'm going back here. This was my excess reactant. This was my limiting reactant. So even though we did use some of the nickel ion to form the precipitate, we didn't use all of it. So here's kind of what we need to do. And you can do this a couple different ways. To find excess nickel ion, we need to figure out how many moles we started with. I'm going to say moles initial, and subtract moles of nickel ion, let's put that 2+ in there, used. And so there's a couple different places we can get these numbers. I kind of know from my calculations up here that the nickel that I would have made here came from my nickel here. And so I know initially the moles of nickel I started with here is 0.03. But let's just maybe take a minute and calculate that out in case you didn't know. If you need to find moles that you had initially, you can go ahead and use that molarity equals moles of nickel over the volume of original solution, and then solve for moles. If we do that, I'll just go ahead and do this out. Moles of nickel 2+ initially is going to be equal to the molarity, which is 0.150 moles, or molarity, my bad, capital M, times volume in liters, so 0.200 liters. That's where I get that 0.0300 mole of nickel ion from. You know what? One of the things maybe you could do here is figure out how would you go back and calculate the initial amount of moles that you had. The tricky part is thinking about how many moles of nickel you used up. But really, I'm going to go back here again. If this is how many moles of nickel hydroxide I created, and I have a 1-to-1 mole ratio of nickel within nickel hydroxide, I'm going to shortcut this. I know this is how many moles of nickel I used. So again, you can do some other calculations for that, but it's better off to use what's right in front of you. And so excess nickel ion is really going to be the 0.0300 moles of nickel I started with minus what I used to make the precipitate, which is 0.0100 moles of nickel ion in there. And again, all of those numbers are there. It's just kind of interpreting how to use them. So when I subtract that, I end up with 0.0200 mole of nickel ion. But remember, now it's in 300 milliliters, or 0.300 liters. So my concentration is actually 0.0667 molar Ni2+. And that is a super long, drawn out calculation for the nickel ion. These ones are pretty easy. This one, you really have to kind of figure out what information you have already, and you honestly do already have it kind of at the top. So if I were to draw in this little corner my reaction vessel, what I would see down here in the bottom is I would see some of my nickel sulfate or my nickel hydroxide in there. So that would be my solid, right? And OH2, I went ahead and drew that again. And then in my solution, I would have some K plus, some SO4 2 minus, and I'd have a little bit of Ni2 plus. But honestly, if I look at this and I look at K plus up here, I really kind of have the same amount. What I have more of is I have actually more sulfate. So I'm going to draw a couple more sulfate in there. This is a super challenging problem. It really kind of tests how well you are able to see how everything fits together. Let's go ahead and do the last two problems. Question 9. I'm going to go ahead and write out this balanced equation. Sodium nitrate is mixed with some sodium chloride solution. We're dissolving it in 100 milliliters of water. So these are actually both solids first, but we're putting them in water, so they're going to dissolve. And then we're going to add excess silver nitrate. Excess. Now, this, you normally don't write 3 reactants here, but I'm going to go ahead and write it because we know these are all spectator ions, right? Sodium's going to be a spectator ion here and here. Nitrate is going to be a spectator ion. So really, when we add this silver nitrate, you're producing a white solid. Think about where that white solid is coming from. It has to be from the silver and the chloride. So spectator ion, spectator ion, spectator ion, spectator ion. It's really just this, AgCl. That's our solid. So the silver is really coming from the silver nitrate. The chloride is coming from this. Here's the problem. We have a 1.50 gram mixture of sodium nitrate and sodium chloride. We don't know how much of that 1.5 grams was sodium nitrate and how much was sodium chloride. There's the tricky part. That's where they're getting you. So if you had an extremely magnified view of the solution, list the species you would see before and after the reaction. So before, we would see some Na plus, some NO3 minus, and we have Na plus coming from 2 different places. I'm not going to write it twice. We would see some Cl minus, and we would see some Ag plus, right? We've got nitrate coming from 2 different places and sodium coming from 2 different places, but those are really the ions we would see. After the reaction, what's going to happen is these two are going to form the precipitate. So we're going to see excess ion, excess spectator ion, I should say spectator ion, and then AgCl solid. But here's another thing I want you to think about. They told you that you were adding excess, where is it? Excess silver nitrate. There it is. Right here, this word excess. So that also means in addition to the nitrate, we have some Ag plus because silver nitrate was an excess. So we're going to see all of the chloride ion getting used up. We're going to have spectator ion, and not all of that is going to get used up to make the precipitate. So just to kind of recap, Na plus and NO3 minus, those are our spectator ions. And then we've got some Ag plus ion in excess. All right, so write the balanced net ionic equation for the reaction that produces the solid. That's only our Ag plus and our Cl minus. All right, now this one we need to think about. Calculate the percent sodium chloride in the original unknown mixture. So going back to this, remember I said we have a 1.50 gram mixture, but we don't know how many grams of it were sodium chloride. This should look familiar. We looked at one of these early on this year, and I said it was going to kind of come back. It was a precursor. So Let's take a look at our solid that we massed out. We massed out 0.641 grams. We're going to start with that 0.641 grams, and we want to calculate percent sodium chloride. So what we really need to know is we need to know how many moles really of that Cl we got. So there's a couple different ways to do this. I'm going to go ahead and start with my 0.641 grams of AgCl. And remember, the first thing we do is we convert it to moles. We know that 1 mole of AgCl is equal to 143.35 grams of AgCl. Now, I'm going to go ahead and use my net ionic equation here. I know that I get 1 mole of Cl minus ion for every 1 mole of AgCl. And I also know if I go back up here, I have 1 mole of Cl minus ion for every 1 mole of NaCl I started with, because that's the only place my chloride ion came from. So I can go ahead and use that. I get grams of silver chloride to cancel, moles of silver chloride to cancel. I know from my net ionic equation, 1 mole of chloride ions are used to produce that 1 mole of silver chloride. And then from my original answer up here, I know 1 mole of chloride ion are in every 1 mole of sodium chloride. Now I can go ahead and use molar mass of sodium chloride. I know 58.44 grams of NaCl off my periodic table is the molar mass for 1 mole of NaCl. That gives me a total of 0.2613 grams of NaCl that reacted. So, by the way, that's probably my last sig fig there. Therefore, if I take that 0.2613 grams of NaCl over my 1.50 gram of my mix times 100, I get a 17.4% NaCl in that original mixture. Done and done. Take a really good look at that. I think that's an excellent AP question. And we're going to do the very last one. Yay, last one. Same thing, except this time pay attention to the word pure. We have a pure compound that has this formula, but we don't know what that metal is. It was dissolved in water, treated with excess aqueous calcium chloride, and got a precipitate. So whatever that M is probably an alkali metal, because if you look at it, it's M2SO4, so it has to have a +1 charge. So here's what I'm going to do. I'm going to go ahead and set up this balanced equation. Calcium chloride is reacting with whatever this compound is, SO4 aqueous. And we get calcium sulfate as our product plus 2, whatever that metal is, Cl. And we know that's aqueous. And again, this is our precipitate. We know whatever this metal is, it's +1. So I know it's +1 minus 1. And I know to balance it, I put a 2 in front of there. I'm just going to write a couple things down. I know this is an excess, which makes this my limiting reactant. I have 1.42 grams of that stuff. I made 1.36 grams of the precipitate. So when in doubt, we need to try to figure out what this is, but let's find moles of calcium sulfate that we formed. So the first step, moles of calcium sulfate. So we know we've got the 1.36 grams of calcium sulfate and 1 mole of calcium sulfate is 136.15 grams. That gives me 0.009988. Or if I'm sticking with 3 significant figures, here's my third one. We could do 0.00998. I think I'm going to go 0.0100 mole. because I actually think that's going to get me close enough. Now, do what you want with sig figs here, but we're really just trying to find the atomic mass of M so we can identify it. Now, remember, the atomic mass of M, another way of saying that is molar mass. So the units that we want here are grams per mole. So if you think about this, we have grams right here. We know we have a 1-to-1 mole ratio between our calcium sulfate and our unknown compound. We just calculated how many moles of calcium sulfate we have, so we also know that we have the same number of moles of our mystery metal sulfate, M2SO4. So if I want to find the molar mass of this compound, I'm going to take the grams of the compound, 1.42 grams, literally grams over mole, over 0.0100 moles of whatever this is. I'm going to say M2SO4, M2SO4. So that gives me approximately 142 grams per mole for the molar mass of M2SO4. Now, the other thing that we have to do is we have to figure out what that mystery metal is. Well, sulfate has a molar mass of 96.07 grams. I'm just going to subtract it. 96.07 grams per mole for SO4. So if I get rid of the SO4, I should just have the molar mass of my M2. And so that gives me 46 grams per mole, but that's for M2. So now I have to divide by 2 to get just plain old M. And so that's 23 grams per mole. And on our periodic table, that is sodium. It's a good one. I actually think that's a really good AP type question too, if they wanted to really kind of have you just take a look at mole relationships and things like that. So work through these the best that you can. This is one of the longer problem sets that we do this year. So keep up the good work and we'll see you later.